Whereas in the last section, we discussed the particle-like nature of light, in this section, we will discuss the wave-like nature of elementary particles, such as an electron. The wave-like nature of matter requires us to introduce quantum mechanics, where we use the Schrödinger equation to describe the electron as a wave. Although we like to think of electrons as elementary particles with a mass and velocity, there are several experiments where electrons are better treated as waves. For example, if we produce electrons from a hot filament and pass them through a double-slit experiment, the pattern we see on the screen looks like diffraction fringes we expect from waves. The wavelength found in these experiments turned out to be inversely proportional to the electron momentum, p, where momentum in classical physics is the particle mass times its velocity. The proportionality constant between the wavelength and the momentum of the electron is given by Planck's constant, where Planck's constant is a very small number requiring the electron mass to be very small to be noticeable. This relationship between wavelength and momentum is known as the de Broglie relationship. We can rearrange the exact same relationship we found for electrons to the momentum in terms of the wavelength we found for photons. Such experiments led to the discovery of quantum mechanics, where we treat both light and matter, such as electrons, as both waves and particles using similar relationships. Although in classical physics we may be more comfortable using velocity rather than momentum, in quantum mechanics momentum is much better defined than velocity. And so for expressions such as kinetic energy, where we're used to 1/2 mv squared, instead we shall use the kinetic energy as p squared over 2m. Also recall that we have introduced the wave number k to conveniently describe the wavelength of a wave mathematically. And so substituting this relationship into the de Broglie relationship gives us simply the momentum is h bar k, where h bar is Planck's constant divided by 2 pi. At the moment, the Schrödinger equation is still just a postulate in physics. Although we have learned enough about the particle-wave duality of both light and matter that we can justify Schrödinger's postulate. We learn from experiments on light or photons that the energy of a photon can be described by Planck's constant and frequency, or conveniently written as h bar omega. Similarly, we found that for both light and electrons, the momentum can be described as h bar k. So in order to satisfy this particle-wave duality, Schrödinger postulated that elementary particles should be described by a wave. We'll call this the wave function. Now recall that the easiest mathematical form to describe a wave is using complex numbers in exponential form, such as e to the I x equals cosine x plus I sine x. We shall use the capital Greek symbol psi to represent the wave function. The wave function represents the probability of finding the electron at a position x and time t. For example, the simplest one-dimensional wave can be described by a constant times e to the I kx minus omega t, where a describes the amplitude of the waves, which itself could be a complex number, k is the wave number, and omega is the frequency of this traveling wave. Now, from our experiments relating frequency to energy and wave number to momentum, we can substitute these into our expression for our wave function, giving a wave function where the spatial dependence depends on momentum and the time dependence depends on energy. If we then consider the x derivative of this wave function, we expect it should have something to do with the momentum p. Taking the x derivative then of this wave function, we bring down I and p divided by h bar to give us I over h bar p times what looks like our wave function psi itself, or I over h bar momentum times psi. We can then use this derivative then to find what is the momentum of our wave function by solving for momentum. Solving for p psi, bringing I over h bar over on this side, we get minus I h bar, because minus I is the same as 1 over I, times the spatial derivative of psi. This form is giving us a recipe to find the momentum of our particle by doing a derivative of our wave function. We can describe the spatial derivative as an operation on our wave function. And so in order to find the momentum, we define a momentum operator, given here as p hat, which performs this derivative operation to give us the momentum. Similarly, the time derivative of our wave function will bring down energy times minus I over h bar times our wave function, shown here, so that we can define our energy operator in a similar manner, which takes the time derivative of our wave function, and that should give us our energy. Schrödinger then postulated his equation in the form of Hamilton's equations, which embody the conservation of energy and momentum in a way that naturally gives Newton's laws. He postulates the Hamiltonian of the system to be the sum of the kinetic energy and potential energy to be the total energy of the system. In operator format, he is postulating that the Hamiltonian operator, which is the sum of the kinetic energy and potential energy terms, should then be equal to the energy operator on our wave function. The Hamiltonian operator, expected to be the sum of the kinetic energy term and the potential energy term, can be described classically as p squared over 2m, and so we expect to use the momentum operator we found over here, and then a potential energy term which may depend on position. The p squared over 2m term brings in now a second derivative of the wave function here, and then we square h bar squared, and we have the 2m from our definition of kinetic energy. The potential energy comes in as v times psi, where recall that psi is related to the probability of the particle at that position. And the energy operator is found using our postulate over here, where it's related to the time derivative of the wave function. The simplest example of a wave function is that given by a free electron wave, e to the I kx minus omega t. Remember that these wave functions are given by complex numbers containing real and imaginary parts. To describe real observable values that we can measure in the laboratory, we will need to use operators. So we will use what we call an expectation value of an operator, such as the expectation value of operator O is given by this expression, which is the integral over all space of psi star operator operated on psi, where psi star is the complex conjugate of the wave function psi. And recall that the complex conjugate is where you replace all instances of I with minus I. Psi star psi, using the identity operator, gives us the probability density of finding the particle at any given position, such that if we integrate over all space of psi star psi, we should find exactly one particle in that all space. In this way, we use psi star psi integrated over all space as our normalization function to derive what the value of A should be, or at least the magnitude of A. Other operators which we had before are shown here, such as the momentum operator, which is given by the spatial derivative of psi, the energy operator given by the time derivative of psi, the Hamiltonian operator given by the second order spatial derivative of psi coming from p squared, as well as the potential psi, where the potential might depend on position, where the position operator is simply by multiplying by the position coordinate. For this simple wave function, one can factor out the e to the I minus omega t to give us a wave function which separates the position-dependent part of the wave function from the time-dependent part of the wave function. The time-dependent part comes from the e to the I omega t up here, and then the position-dependent part will be the a e to the I kx. It is left as an exercise to show that using the energy operator given by the time-dependent derivative of the wave function, using this simple wave function, one can show that the energy is equal to h bar omega. For most of the cases we will study in this class, we will be able to separate the wave function into a form with a single frequency or single energy, such that we can rewrite the Schrödinger equation into what we call the time-independent Schrödinger equation, which is given by h operator psi, e psi, where we have changed from the time-dependent capital psi to the time-independent or only spatially dependent lowercase psi. And in doing so, we have replaced the operator energy with the simple scalar energy E equals h bar omega. Then, using this free electron wave for psi and the operator for the Hamiltonian, one can derive the energy equals h bar squared k squared over 2m. And then also from the momentum operator, one can confirm that the momentum is h bar k. The wave function psi has to have certain properties in order to be a valid wave function. For example, it must be a single-valued function. So this curve is not a valid wave function because it doesn't have a single value at a given point. The wave function must also be continuous, and so this discontinuous function here is an unacceptable form of the wave function psi. The first derivative of the wave function should also be continuous. This wave function here has a cusp indicating a discontinuous first derivative, which would only be allowed if the potential is infinity. Having an infinite potential allows the second derivative to become infinite, enabling a cusp. In summary, we will spend this class discussing the time-independent Schrödinger equation, where the time-dependent wave function is separated into a time-independent wave function, and the time dependence is taken into account through a single energy, E equals h bar omega. In this way, we will solve only the time-independent Schrödinger's equation using the time-independent lowercase psi as a wave function, where for our Hamiltonian, we have minus h bar squared over 2m, the second derivative of psi with respect to the spatial derivative. Then we have the potential. We can bring over the e as a constant and make it potential minus e times psi equals 0. At times, we will want to solve the time-independent Schrödinger equation in 3 dimensions, which means this second derivative is actually a Laplacian, which is given by the second derivative with respect to x, plus the second derivative with respect to y, plus the second derivative with respect to z. And our potential also might include x, y, or z dependencies. But we will keep our energy to be a constant because we are separating the time dependence out of the wave function.